All right, so question number 7 on your exam. Switch my share. Question number 7 reads, what is the pressure of gas in atmospheres if it was measured to be 312 torr? So this is really a conversion where you're going from torr to atmospheres. So this is a conversion that you need to know. 760 torr equals 1 atmosphere. So the dimensional analysis would look something like this: 312 torr, 760, 1 atmosphere. And you can kind of make an approximation by saying, well, 50% of torr, or 50% of 1 atmosphere would be 380. And this 312 is less than 380, so it's pretty reasonable to say that you want to pick a number that's close to that. And your best answer is answer option B. Question number 8 reads, a sample of 0.8 or 1.8 moles of gas has a volume of 2.9 liters. If the volume of the sample increased to 3.6 liters, how many moles of gas are present in that 3.6 liter container? So to solve this question, I think that an effective approach is to say, well, I'm going to be looking for a number that is greater than the volume that I currently have. And ultimately, you can come up with an equation where you look at volume and number of a gas, or sorry, the volume of a gas and the number of moles of a gas. And that law is Avogadro's law, which gives you the number of moles of a gas over the volume of a gas is equal to the number of moles of a gas over the volume of a gas. And so what we would want to do is say 0.18 moles divided by the volume that occupies, 2.9 liters. That is equal to X, because we don't know how many moles are in the total, divided by 3.6 liters. And so what we would plug in is 0.18 divided by 2.9 equals that big number there, times 3.6, and you get X, or N2, is equal to 0.223 moles of gas. And so your best answer then is 0.23, or answer option A, which I'm going to go ahead and change. So the exam that you guys are taking will actually have the 0.22. All right, so my next question on this exam is, if a container is sealed with an unknown gas inside, that the container is heated, how will the pressure change, provided that no gas is added or removed and the container does not change in size? Okay, so we're heating it up. You're heating a closed system. What's going to happen to the pressure is going to increase if the volume remains constant. So C is the correct answer for that. Next up is number 10. The pressure of a gas increases as its volume decreases, assuming constant mass and temperature. This is best defined as, the correct answer is Boyle's law. Next up is 11. If the theoretical yield of a substance was 22.6, but the actual yield is 18.6, what is your percent yield? All that you do there is 18.6 divided by 22.6, and you get 0.823. Multiply that by 100 to give it a percentage, and you're looking at B as your right answer. I'm going to continue on for a couple more questions. Number 12. How many moles of H2O can be generated if 15 moles of C3H or C3OH react with 4 moles of C7H6O2? So for this question, what you need to do, and I'm going to go ahead and put this all together, is look at your mole ratio. You see that 1 mole of C7H6O2 reacts with 1 mole of CH3OH. If you're given 15 moles of CH3OH and 4 moles of C7H6O2, and your balanced chemical reaction gives it to us a 1-to-1 ratio, well then this is easily identified as your limiting reactant. And since that's the limiting reactant, then you're going to produce only that many of the product, or thinking about the ratio of your product. So you got to look back at, well, what is my ratio of that reactant with lower quantity, the C7H6, what is that ratio to my product that I'm being asked about, H2O? Well, that's a 1-to-1 ratio. So your correct answer would be D, 4. So in that previous chemical reaction, we're going to change it up a little bit. So I'm going to jump back over here. We've got C7H6O2 plus CH3OH. This ratio is a 1-to-1 ratio that we've got. The question that's asked, number 13, is from the balanced chemical reaction in the previous problem, what mass of H2O can be generated if 4 moles of this react with 15 moles of this? Okay, so this is our limiting reactant. It is still our limiting reactant. We're going to make 4 moles of H2O. If you know the molar mass of H2O, then you can say this times your molar mass. Your molar mass of H2O is 18. 4 times 18, 72. So your correct answer is C. Okay, so moving back, question number 14. From the balanced chemical reaction in question number 12, how many moles of H2O are produced if 15 moles of CH3OH react with 412 grams of C7H6O2? Okay, so this is a little bit trickier. This question is giving you a mass and it's giving you a number of moles. So what we need to figure out is 412 grams of C7H6O2. How many moles is that? Is that 16 moles? Is it 75 moles? Where are we? So I'm going to do my molar mass for C7H6, which is 12. That's the mass of carbon, 12 times 7, plus 6 times 1 for hydrogen, so plus 6, plus 32, which is our mass of our oxygen. And we're getting 122 grams of C7H6O2. That's 1 mole. So I'm going to take 412 divided by 122. And I'm going to get 3.4 moles of C7H6O2. Now, again, I'll look at my reactants. I've got 3.4 moles of this, and again, 15 moles of CH3OH. So how many moles of H2O are going to be produced? 3.4 moles. So my correct answer for this question is none other than answer option D. Okay, question number 15. What is the pressure of a gas in atmospheres if the manometer that you're using reads 760 millimeters of mercury? Well, 760 millimeters mercury is equal to 1 atmosphere. Number 16. A balloon holds 4.5 liters of helium at 32 degrees Celsius. The balloon is then put into a cold van for delivery. The balloon and the helium drop to a temperature of 3 degrees Celsius. How large is the balloon now? Okay, so for this question, we need to use another law. We're using a law where we're relating pressure or volume and temperature. So that is T over V is equal to T over V. So our initial temperature is 32 degrees Celsius, but we need to convert that into 305 Kelvin. Our volume is 4.5 liters. This van has a temperature of 3 degrees Celsius, which is the same as 276 Kelvin, divided by V, or X in this case. So I'm going to say 305K, or 305 divided by 4.5. Okay, so we're looking at 67.8 is equal to 276 divided by X. Multiply each side by X, I get 67.8. X equals 276. Divide each side by 67.8. And I get 276 divided by 67.8 equals our new volume, 4.07, which if we look at our answer options, our most attractive and viable option is that answer option D, 4.1 liters. Okay, next up, a balloon holds 4.5 liters of helium at 32 degrees Celsius. This looks very familiar. It reads the exact same, but the question is, knowing that the gas is helium is essential for successfully calculating this answer. No, it's not. That is a false statement. When we did this calculation, we didn't even mention that it was helium. So we move forward with B as the correct answer. What is the pressure of H2 gas if you have 0.412 moles of it at 16 degrees Celsius in a 3.25 liter container? Okay, so this question, we've got, moving forward, we've got PV equals nRT. We've got a pressure that we want to know about. So we're going to rearrange this equation to be P equals nRT over V. We don't know our pressure, but that's what we want to solve for. N is 0.412 moles. Times R is 0.08206. And T is going to be 273.16 plus 16. So that would be 289.15. Divide all of that by 3.25 liters. And we get 0.412 times 0.08206 times 289.15 divided by 3.25. And ultimately, our pressure that we get is 3.0. Not too surprising, but this question, when we look back at this, it's not too surprising because look at our numbers. It was 3. So really this question was asking, do you know the units that the ideal gas equation uses? And a little bit of a secret is there's our R value. We've got a volume, we've got a pressure, we've got number of moles, and we've got temperature in Kelvin. So that answer is B, 3.0 atmospheres. And that one should be one that you're pretty comfortable with. Number 19, how many moles of a gas are present when the pressure of a system is 712 torr, the temperature is 205 Kelvin, and the volume is 6.8 liters? Okay, so this is another ideal gas equation question, but we're rearranging things. What we're asking for is number of moles, or N. And the ideal gas equation, PV equals nRT, is rearranged to be PV over RT equals N. So I'm going to plug in my pressure. Well, my pressure is 712 torr. I need to convert that to atmosphere. So 712 divided by 760 equals 0.94. Next up is my volume, which is 6.8 liters. My R value is 0.08206. And my temperature is 205 Kelvin, so 205. I don't need to do a conversion there. So 0.94 times 6.8 divided by 0.08206, 205. And the correct answer that I get, 0.94 times 6.8 equals 6.392. 0.08206 times 205, 16.8223. I don't like my phone here. It's as a calculator. 6.392 divided by 16.8223. I get 0.37997, or 3.0 0.80 times 10 to the negative first. So my answer options that I provided myself with, I need to look back at on the actual exam. So 0 to the 1. Okay. But the correct answer for that is answer option B. And then the next question is number 20, which reads, if the pressure of a container goes up, the number of moles remain constant and the volume remains constant, what happens to the temperature? So if the pressure is constant, nothing in the system changes. Or sorry, if the pressure goes up, the number of moles of the substance and the volume remains constant, what's going to happen to the temperature? Well, we've actually already kind of seen this question where we saw, so sorry, if the pressure goes up, the temperature is going to go up as well. All right, well, that wraps up 2.2. I hope this was helpful, and I hope you have a good one.